Hey, good evening, Gen Chem 1. I love it. Let's do some more with some chemical reactions. I'm so excited. We're going to start. This is the first video for chemical reactions. So let's start by doing some defining. In a chemical reaction, I'm so excited. Isn't that what chemistry is all about? We've had how much of our semester before we actually got to chemical reactions? Isn't that crazy? So this is so exciting. Let's tackle some chemical reactions. Let's start with some basic definitions. We've got typically on the left side of our reaction, this is our reactants. Okay, and on the right side are our products. So, and then we've got an arrow in between. Now, our chemical reactions are often written in this formula unit type. This is called a chemical equation a lot. We're going to use it in math. So sometimes this arrow, we can picture it's like an equal sign. And this is literally an equation that we're going to use in math. And then what this arrow, there's actually meanings to this arrow. So a straight arrow like this is what we're going to start with in this class. What this actually assumes is that all of your reactants turn into all products. So this is a good place to start. You're assuming that all of this turns into all of this, and that's where we're going to start. We're going to start there using our math and our defining, and we're going to start there classifying our reactions. But in real life, that almost never happens. What you tend to have is reactions that go mostly forward, and then you still leave behind some starting material. So sometimes you'll see an arrow like that. And then sometimes you have reactions that just barely work, and they mostly are starting materials. So then your arrows will be like that. You can kind of think of it this way. In your arrows, size matters. You know, your size matters. And then you'll often see an equal 50-50 arrow. This is an equilibrium arrow. We're going to spend a lot of time with that in Chem 2. You'll see that in a lot of your biology classes. It doesn't mean that both sides are equal. It means that you're in equilibrium. Okay, so for this class, we're going to start with our arrow just looking like that. But if you see some of these other arrows, they're just getting a little bit more specific with their reaction. And then as we're going with our reactions, now that we've kind of defined what they're looking like, we've got to add some math to them. We've got to figure out how they're kind of happening, what they are. We're going to spend the rest of this semester looking at reactions and adding as much information as we can. So let's start. I'm going to just take a second and erase this. So if you need a screenshot for a second, I am going to add a little bit more information here. We've got a couple laws to the universe we've got to tackle. One of those is that we cannot create or destroy matter. This one is really important. We cannot create or destroy matter or energy. Now this is going to carry us through Unit 4 as well. When we look at thermodynamics, we're not going to create or destroy. We're just going to shuffle it. It's going to change. We can undergo changes, but we can't actually create it or destroy it. So this is fundamental in our chemical reactions. Why? Well, because we're going to take a look at every single chemical reaction, and I'm going to teach you to do something called balance that reaction. So we are now going to have trust issues. From this video on, you cannot trust me. I am going to give you reactions that just look like this, but that equation is not valid yet. We have to balance it. So from now on, from all of the rest of our videos to our homework, to our exams, to our final, you have to stop, and we're going to take a look at this reaction and make sure it's balanced. Now, what does balanced mean? All right, we're going to picture that on this side, we've got methane. Well, we drew this in Unit 2. We know what that looks like. Okay. And then we also know from this unit that that is 1 carbon and 4 hydrogens. And then we've got oxygen. We know from unit 2 it looks like that. And then that is 2 oxygens. So whatever is on this side of our equation, right here, literally has to equal what's on this side of the equation. They have to equal. So if I have 1 carbon, 4 hydrogens, and 2 oxygens, the only thing that happens in a chemical reaction is that we rearrange those bonds. But the actual number or amount of those atoms must equal on both sides. And that's important. Remember, we're not creating or destroying any kind of matter. We're literally just rearranging bonds. So this is what a balanced reaction means. You're going to stop and make sure you've got the same number or amount of atoms on both sides. So let's just double check that. All right, let me erase this for a second. Let's double check it. So I've got 1 carbon, 4 hydrogens, and 2 oxygens on this side. Let's draw a little line. So then on my product side, it looks like I've got carbon dioxide. We drew that in unit 2. Oop, no lone pair there. And lone pair go right here. All right, so that is 1 carbon, 2 oxygens. And then we've got water, or dihydrogen monoxide. And in our water, we've got 2 hydrogens and 1 oxygen. So total on this side, okay, we've got 1 carbon, 1 carbon. Beautiful. That matches. That is balanced. Okay, we've got 4 hydrogens. Well, son of a motherless goat. Only 2 hydrogens on this side. That is not balanced. This equation is not balanced. We're breaking laws of the universe right now. And then let's double check our oxygens. We've got 2 over here, and holy crap, we've got 3 on this side. All right, so at this point, as this is drawn, this is not balanced. That means we can't do anything with it yet. It is not ready for any kind of math, something called stoichiometry. We're not ready yet. This equation is not done. We have to fix this. We have to balance this reaction. So how do you do that? Well, take a screenshot for a second. I want to just literally spell out what's in each side. What I like to do is add up what's in each side. And then just make sure, like we just did, if we are balanced or not balanced. All right, so remember, we were picturing in our moles unit every one of these atoms and molecules as separate beings, because in a reaction, we're going to break all those bonds and rearrange everything anyway. So our pieces have to match on both sides. So if I've got 1 carbon, 4 hydrogens, and 2 oxygens, on this side, we have to get to a place that matches. And we could tell right away when you spell it out like this that they don't match, and this is not balanced. So we're going to take the rest of this video to balance our reactions. And I stole an idea from a textbook, but I drew my own. I wanted to give a little graphic. So if we're looking at our reaction, literally, these are our atoms. My little green there, those are your hydrogens. This little black ball is your carbon. And these 2 very inappropriate looking red balls are your oxygens. Okay, so literally, whatever stuff you have on this reactant side, you have to have on your product side. And when you just look at it visually like this, well, we're missing some of these greens, right? We're missing some of these hydrogens, and all of a sudden we've invented a 3rd red oxygen. That can't happen. And then we've got our 1 carbon. So as a visual, this is not balanced. So we can't say that this is equal yet. All right, but we also learned in unit 2. Now here's the here's the tricky part out of all of this. Didn't we learn in Unit 2 that these fixed ratios are up to Mother Nature? Okay, we just spent a video talking about those fixed ratios, and that fixed ratio, like in something like sodium chloride, that is 1 electron leaving sodium and going to your chlorine. That is up to electrons moving. That is up to Mother Nature. That's not up to you. So how in the world do you actually balance a reaction? You cannot change that fixed ratio. That is a no-brainer. We cannot do that. So in other words, CH4 has to say CH4. You can't change it to CH2. CH2 doesn't exist as that. Okay, so you can't change the O2, the CO2, or the H2O. So how do you balance a reaction then? What's fair game? Fixed ratio has to stay the same, but amounts can change. All right, so what does that mean? Well, that means what if we have 1 methane and 2 oxygens? Or what if we make 2 carbon dioxides and 3 waters? Those can change. So it is totally fair game to use amounts like this to balance your reaction, but you cannot change these. Those fixed ratios, those little subscripts, those stay the same. That is what makes that molecule, but we can change our amounts or those coefficients out front. So how do we actually balance this reaction then? We can tell visually that it's not balanced. So let's scroll down just a little bit and let's see how we can balance it. So what we really need is to end up with the same number of those atoms, or of each atoms on both sides. So we've got to end up with the same number of hydrogens, same number of oxygens, and same number of carbons. So how do you make that happen? Well, if we look at the second little visual, when we started up here, we weren't balanced at all. But now if you look at the second one, well, what if we've got 4 instead of 2 oxygens? Now over here, we've got 4 oxygens. And then here's our 4 hydrogens. So we already had 4 hydrogens over here. And then we still had our 1 carbon. So now on both sides, this is now equal. Your atoms on your reactant side is equal to your product side. That's awesome. That is what a balanced reaction is. So how do you write that? Let's write it, and then we're going to come back to, let's write it up here. How would you write that then? You're going to say CH4. Okay, we kept that the same. But now our oxygen, we ended up with 2 of them. Okay. And then our carbon dioxide, we still had 1. But our water, we had 2 of them. So this is now a balanced reaction. Okay, I love it. All right, now do you have to draw out all these balls each time? No, I just wanted to have fun with my drawing program. So let's go up here and try my little method. We could literally take, let me show you a second way how to do that. We can literally take and monkey with both sides of the reaction until you get them to balance. That's what I typically do. Every once in a while, a student will ask me, is there an algebra formula? Can I plug a formula in and figure this out? Maybe. I tend to solve them like a puzzle. So I kind of start on this side and say, all right, I've got 1 carbon, 4 hydrogens and 2 oxygens. I've got 1 carbon, 2 hydrogens, and 3 oxygens. And then my general rule of thumb is I start with the most complicated formula. And so I'm going to pick the CH4. Why not? And I'm going to do the least complicated formula last. So let's do oxygen last. So with my CH4, my carbon, those are equal. I don't have to do anything. But now the hydrogens are not equal. So if I've got 4 on this side, how do I get 4 on this side? Well, the only place you have hydrogen is your water, so you're going to have to multiply that whole thing by 2. Okay, but that's not H2 by itself. You have an oxygen there. So you now just multiply that oxygen times 2. So how many oxygens do you have now? Now you have 4. Okay, you've got 1, 2, 3, 4. So don't forget to do this part. Remember, that's not by itself. You got to include the oxygen. Well, now we go back to the other side. So we've got our hydrogens equal, but our oxygens aren't quite equal. How do we get them equal? Well, what if we could go to 4 oxygens on this side? How do I do that? I'm going to put a 2 right there. And now we've got a balanced reaction. I love it. That deserves a sparkle pen. Okay, so let's spend the rest of the video just trying that. Let's just balance some reactions. Before we go on to anything, we have to take reactions and balance them. That whole thing has to be balanced. I like to think about it this way. This is a little guide for you. Your reactants and your products, they are an equation. We are going to get to a place where they equal. Okay, our number of atoms are going to equal. That's what we just did in our balanced reaction. Okay, now here's the fun part. If your total atoms balance and your atoms are the same on the reactant side and the product side, then that means that that total mass is also going to be the same. Okay, that's trippy. Look at this. You didn't change the amount of stuff you have. You just rearranged your bonds. So your total mass, all of this, should be equal in both sides of your reaction. Now, the one thing that does not have to be equal is moles. Moles does not have to equal. Remember, mole is your particles. So your particles can rearrange. Now, if we look at all sorts of reactions, you don't have to have the same number of particles, meaning atoms or molecules. You do have to have the same total number of atoms, but in our reactions, we're rearranging those atoms and forming different particles. So your moles don't have to equal. They might, in this case they do, but they don't always have to, and we'll see that in other reactions. So that one is pretty trippy. Let's put a sparkle pen around that. So how do moles fit into here? This is what's beautiful. If you write a nice balanced reaction, just wait for it. Let's write it out again. All right, let's put in our 2 here and our 2 here. Your balanced reaction is a chemical equation. This is an actual equation, and we are going to do math with it. And what we're saying is 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. So this is your mole ratio. Oop, I highlighted in the wrong spot. So when you balance your reaction, you have just created one of our favorite things, and that is a mole ratio. We are going to use that in math. So be careful. Your mass and your atoms are going to equal, but your moles don't have to, because your actual particles can change. All right, let's put this to the test. Let's just have some fun. Let's balance some reactions. I put a couple of examples here. I thought we could just try them together and then you can practice some in the homework. All right, let's try my little technique here. Let's spell out what's on each side. So in this case, I'm going to take booze and light it on fire. So our ethanol, we've got 2 carbons in that first ethanol. We've got 6 hydrogens. And then how many oxygens? Remember, this is total. So we've got 1, 2, 3. 3 oxygens. Okay. All right, let's spell out the other side. We've got 1 carbon. We've got 2 hydrogens. And how many oxygens? 1, 2, 3. Okay. Well, that's not bad. That seems pretty reasonable. All right away, let's start with the most complicated formula. That's our booze. That's ethanol. All right, right away, are our carbons even balanced? No. So how are we going to balance that? Well, we're going to need to get to 2 carbons. Let's start there. Let's try it. The only way to do that is to add a 2 right there in front of our carbon dioxide. Well, that didn't change just carbon. That changed your oxygen as well. So what does our oxygen change to now? 5. Okay. Ooh, all right. Now we're getting somewhere. So now our carbons are balanced. Let's try to balance our hydrogens. Our hydrogens are not balanced. We've got 6 on this side, 2 on this side. Okay, how do we get to 6 then? Let's just start there. All right, let's see. Let's try to get to 6. We're going to have to put a 3 here. That gets us to 6 hydrogens. Oh, that monkeyed with our oxygens again. So now how many oxygens do we have? I'm getting 4 here and 3 here. So we just went to 7 oxygens. All right, so our carbons are balanced and our hydrogens are balanced, but our oxygen isn't. We have 7 on this side and 3 on this side. Well, son of a motherless goat, our oxygen is an O2. So how do we get to 7? Well, that would have to be a fraction. You would have to have 7 halves in front of that oxygen. Oh, let me write that with pink. Follow my pattern. Okay, 7 halves oxygen. Now, typically when we balance reactions in Gen Chem 1, we don't leave a fraction. So this gets us to a balanced reaction. We just don't want to leave that fraction. We want to fix it. So how do you get rid of a fraction? You have to multiply the whole thing by your denominator. So what does that end up being? Well, we've got our booze, our oxygen, carbon dioxide, and water. All right, we are about to get sassy here. So we've got 2 of these, 7 of these, 4 of these, and why do I have a 3 there? That looked like a 3, didn't it? And we have got 6 here. Okay. I love it. I love it. What do you think? So let's add everything up. This one was a little bit sassy. Let's add everything up. We've got 4 carbons. We've got 12 hydrogens. And we've got, holy cow, 16 oxygens. Let's try this side. 4 carbons. We've got, 12 hydrogens. And then how many oxygens? 8 plus 6, 14. Does that seem right? So we are off in our oxygens, aren't we? All right, let's double check our oxygens up here. Let's make sure we're not going too crazy. How many oxygens do we have up here? we need to go to 7, or do we? So we've got, I had a 2 there. We've got 4 oxygens, 3 oxygens. Yep, we need to go to 7. So wouldn't that be 7 halves? So this is 14, 16. So this is 8. Why don't you guys try it and then